am Julie Costanzo. I'm from Strasbourg University, and I'm interviewing Professor Leon Sanche today for the Radiation Research Society. Professor Sanche did his BSc in University of Laval in Quebec, then followed by a PhD in Yale University, and he became professor at University of Sherbrooke. So, hi, Professor Sanche.
Thank you.
Thank you for being
Well,
here.
thank you for inviting me to say a few words.
So, can you talk about your career?
Yes. Well, just to make it into in a few words, what I did basically in my career was to try to find out and understand how electrons of low energy, and that means energies which are lower than about 100 electron volts, how these electrons would interact with matter in general, but more specifically with biological matter in the later part of my research, and in the former part of my research in simple system, but always in the condensed phase, except for my PhD degree, which I did, as you mentioned, at Yale University with a man called George Schultz, who was at the time the world expert on interaction of low energy electrons with molecules which were isolated. This is electron molecules interaction. It's completely isolated. That means you're studying gases. And at the time that I arrived, he just had discovered one of the very basic mechanisms of interaction of low energy electron with matter. And this was that for a molecule or an atom, the electron is captured temporarily by the atom or the molecule for a time which is much longer than the usual scattering time. And this creates a transient negative ion. This basic principle of transient negative ion was quite important, and at the time he was nominated for the Nobel Prize to have found this, but unfortunately he died a few weeks, not a few weeks, but a few years after, before anything happened. I don't know what would that have happened, but I think it was seen there as a very basic contribution in physics at this time. So that's where I started my career, doing this as a PhD student.
Okay, so you got your position in the Department of Nuclear Medicine and Radiation Biology in Sherbrooke. So what happened since then with the low energy electrons?
Well, yes, I got this position. It was not my intention, I have to admit, to go in medicine or anything that had to do with medicine, because this was the faculty of medicine. But they had a big project in Sherbrooke, and I had a flat tire with my car, so I stopped at a friend in Sherbrooke just before just during the time they repaired the tire, you see. And he had this position for a professor that would lead a project to have a cyclotron. But this was in 1970, and nobody really had a cyclotron in the Faculty of Medicine. You know, a medical cyclotron, the term did not even exist. So, anyway, I think myself and other people in the department, including a few other physicists, we wrote what I thought was a pretty good proposal to get the cyclotron, but the government didn't think this was very serious, you know, to have a bunch of physicists who wanted to have fun with the cyclotron in a faculty of medicine, you know, no. So that didn't work, and this is what started the low energy electrons in a way, because then I said, what am I doing here? You see, because this is nuclear medicine, and I think there's no big project, so I'll just go somewhere else. So, but this was nuclear medicine and radiobiology, in which, as you know, there is radiotherapy. And at that time, they told me, well, you see, if you want to stay here, you have to do something, because I was not doing very much then. I was looking, what do I do here? And they wanted me to do patient planning and this sort of thing. And I said, I didn't want to do that. You know, that was not my career goal. But I look into it, you know, and I said, my God, I don't think we really understand what is going on there. So then I look at it from the start. You know, we produce ionization. It's called ionizing radiation. So you produce ionization. So you have an ion, and you have a secondary electron. So I made a quick calculation with the Born approximation and so on, and from this simple calculation, found out that most of the electrons would have an average, the average energy of the distribution of the secondary electron would be about 10 eV. Okay, and later this was confirmed by Laverne and Pinblott in a very sophisticated calculation, or at least much more than mine. And later I found out that there were quite a few, well, there was some physicists in the field that clearly had identified this as a major issue in radiation physics, and knew that. But many people had said this is very important to study low energy electron, but there was nobody who actually did it, you see, and this is my career, is to actually do it, you see. So I started, well, the problem was I had a good background, but it was just in gases. So I had to start studying in condensed matter, because humans are condensed matter, and complicated condensed matter also. So I had to start with simple system in condensed matter. And so what I did was just to build equipment, because this was all new, because nobody had tried so far, or maybe they tried, but it didn't work, because I didn't know of anybody who had done experiments in condensed matter with low energy electrons. So actually, so then I had to build equipment to do that, and I did that in Sherbrooke. When I arrived in Sherbrooke, of course, in an hospital, it was worse than a cyclotron. I think there was really nothing to do this. But this I like, because I like to build system and so on. So I started to buy specialized equipment to do these experiments. So your question is, what did I do once I'm in Sherbrooke? So what I did is, for about 1980, I would say, or maybe a little bit, no, I was in 1975, it started. And from that year, then I started to build the equipment and do experiment in simple system, and try to and started to discover very basic rule on how low energy electron interact with condensed matter. And this lasted at least until 1995. So 75, that's 20 years just doing that. So I think the financement was, the people that financed me were patient enough that I'd say one day we can study biomolecule. But I had also funds from other sources, because it was much more easy to apply these interactions to other systems which are more simple than biology. Biology was the hardest, right? So there was nanolithography, there was astrochemistry, there was dielectric aging for high voltage cables. So I did research in many fields where this could be applied. And today these fields are developing, or they're already well developed. And this was taken up by other groups, because my goal was to study biomolecule. So this is this first step. And would you like me to continue, or you have a specific question?
Yes, I have other questions. So I met you in Sherbrooke a few years ago, and you're working right now more about biological systems. So what is exact your your I don't know, like your experiments with DNA and.
Well, that's it. In 1995, then we started to build some equipment to be able to work with DNA and large biomolecules. And as you probably know, in the year 2000, we had an article in Science.
Yes, I know.
That said that shows very specifically that these electrons could damage DNA, which people thought before they wouldn't do anything. And not only that, but we showed that as a function of electron energy, it had a very strong oscillation in the yields of damage, and that was due to the presence of these transient negative ions in the DNA. So they were there in the DNA, and we had the background to explain a lot of the physics that came after. So after, from 2000 to very close to now, I would say. I should say now because the basic work is always continuing. What we did is we applied these basic principles that were studied before in simple system to big molecules in biological systems and combination of molecules and so on. And it's quite interesting. It's absolutely fascinating. And that's why I just stick to that. Because, you know, if you take a high energy electron, for example, that's just a very fast charged particle. If you take a fast proton in proton therapy, it's just a fast moving particle. And fast moving particles behave like electromagnetic radiation because the molecules see a very fast moving charge and that produces electromagnetic radiation. So finally, I didn't find that very interesting. But once you look and you see this distribution of low energy electrons, and that this is the important part, another very important part with the ion that produce the radicals in creating the damage, and you see that this has never been studied, and also it's very interesting because this electron now has a wavelength which is of the order of the dimensions of the DNA and even the interstrand distance and the distance between the radicals, not the radicals, but the small subunit in the DNA, then you have all kinds of quantum effects because of this wavelength, and it becomes really tricky in a way, difficult to predict, but you have all kinds of nice phenomena that you find in solid state physics that you would find also in the DNA. For example, we find that one of the major mechanisms to break a strand in DNA is not a direct hit for the electron, but rather a capture by the base, which then transfers the electron to the phosphate unit. And now we know, more recently, we found that the transient negative ion can be created in an excited state, and sometimes the excitation, the electronic excitation, and the electrons separate. So one is causing one strand break, the other is causing another strand break, and then you get a double strand break. So all these things are coming in and explaining how these secondary electrons, which most of them are of low energy, are creating the damage. And so I think your question is more when you were in Sherbrooke, you see that we're much more biological now in what we do.
Small animals and
exactly. Well,
that cancer, I saw some of your students working on that.
Yes, now we even have a protocol now and money to do research with patients from these basic principles. But this is the whole idea, is that I'm absolutely convinced that there will be a lot of application of this, but it takes a lot of time. You see, it's not even in the textbook now that this is not just OH radicals and a few radicals created by the initial ion that you get in the beginning, but you also have these electrons, you see. So before everybody starts to think about in terms of low energy electron, it will take time to really get there. But if you think about the application, there is a general application, I would say, which is simply we generate, for example, the cross-section, that is the probability to create certain damage in DNA or with a particular subunit of DNA or other biomolecule. And this is just to give the parameters for people who are doing Monte Carlo calculation to put in the Monte Carlo. But if you think that most Monte Carlo calculation, I think, stop around 20 electron volts, well, they're missing a large part of the deposited energy that could do a lot of damage, but it's just not there, right? So in doing this, so this is the, you know, any radiotherapeutic treatment should include in the dose calculation some good Monte Carlo calculation that has the values of the parameters and the damage created by low energy electrons. I
agree. There's lots of work to do in this particular.
This is more of a general way to look at it. But it's not very spectacular. It's just the advancements of science. But how we're going to apply these basic mechanisms, I think it's only starting. It's the tip of the iceberg of what we did. And one of the things we looked at is chemoradiation therapy. Because if we measure the yields of DNA damage without a chemotherapeutic agent, like cisplatin, or we also study oxaliplatin and other platinum compounds, they bound to DNA, and the probability can go up for certain damages as much as a factor of 3. Now this is enormous, you see. So this shows the advantage of looking at the details with low energy electrons, and it may be responsible for the effect which is super additive when you use radiation and chemotherapy, because it's not linear because of this effect of low energy electron. Is there other effects? I don't want to say it's just that, but we've shown that there was a big effect here. But the question is, this is not going to convince biologists, right? So this is where the biology experiment came in. Okay, because if what we're saying is true, these transient negative ions do damage on a time scale of femtoseconds. So it's extremely fast. If it's another mechanism saying that the cell is weakened by the chemotherapeutic agent and so on, it's biology. And that takes over times of weeks. Sometimes it could be, it depends, could be hours, could be minutes, could be years, we don't know. It depends. But this is instantaneous. And what this is telling us is that if effectively these low energy electrons are there and they are doing the damage, then the best chemoradiation therapy could be done when the amount of the chemotherapeutic molecules, their amount would be maximum there will be maximum binding of these molecules to the DNA of cancer cells. So this was the experiment that you know about that we did with TT-TIP on using the ACT colorectal cancer cell, human colorectal cancer cell, that were transplanted in mice. And there we look in the literature to find out where was this maximum. And we found all kinds of data, but nobody had ever measured where is the maximum of binding to DNA. So we did it, and we found, I think it's something like 36 hours or something like that. Maybe it's not the exact, but it doesn't matter. There is a time where the maximum, you have a maximum of binding of, let's say, cisplatin to DNA. So we irradiated many mice at different times, and we found out that the best treatment was exactly when it's maximum in the cancer cell. And so it's no definitive proof, but it correlates very well with the basic science.
So there is a time window where the radiation is
Right.
efficient, more efficient. Okay, that's great. So do you have any other details that you want to talk about?
Well, I think the other thing where this is going, yes, chemoradiation therapy, I think we have to do more than just doing dose calculation, because the dose is the same if you have a chemotherapeutic agent. So in terms of dose, you say the treatment is the same, there is no timing, there is nothing. You calculate the dose, the traditional radiotherapy, and the patient receives chemotherapy, is the same thing. Okay, now we have a clinical protocol where we're going to test at different time also to see if we can reach in humans this maximum. But the other thing is that one of the things which is becoming more and more popular is to go to targeted radiotherapy. Because what you want to do in targeted radiotherapy is to have to send the radiation with a particular vector molecule directly on to bind to the cancer cells. And in the very sophisticated ones, it could enter the membranes and actually go to the DNA or very close to it. And if you're that good, and this is just more or less of a dream for the moment, but if you can push it to this level, this means that you'll be able to use OJ electrons. And most of these are very low energy, so there's not even a question of saying, well, high energy radiation produces low energy electron. They're all low energy, except for, there are of course some are keV and so on, but these, even at this energy, the amount of secondary low energy electron which is produced is just so dense and tremendous. So there would be an application, because what dose means at this stage is not very important, in the sense that, well, you can calculate, first of all, you may want to calculate the dose in this microscopic volume that you have, or nanoscopic, but you may also want to just tell how much DNA damage is going to be, which might be more significant. And so I can see a lot of development there, and this is the field in which we are working now.
So you're working with radiation, kind of internal radiation, and imaging, molecular imaging, for example, or not?
Yes.
Okay.
Yes. Well, this is
so both diagnostic and.
Yes, we started with, we didn't start with OJ electrons. We started with fluorine-18 labeled compounds, and with FLT, with fluorouridine labeled with fluorine, and with this goes into the metabolism of the cell, and there's quite a bit in the nucleus, goes in the nucleus, and so we use the positron, which are emitted, as a way to damage the cell, to do the radiotherapy. And the annihilation of the positron gives you the image, so you have both. But what you have also is a very short distance, so you can treat locally, as long as it gets there. But what we do is we believe in conduction enhanced delivery, which means the direct injection of the radioisotope in the tumor. And this is a practice which is more recognized in chemotherapy, but I think that why not do it also with radiotherapy? And on that we have, we submitted an article recently there to Nature Medicine on this. And so there might be some interesting experiment to be done at that level. But I think it's only starting, and if I'm going to summarize everything that I did, not that I did, but maybe what I said. I think that it's, you know, I come here and I see, well, it's true that I'm maybe not that good at understanding all this biology, but I see, I come here for many years. I came in the beginning, I think it was 1980, I came first to a radiation research meeting. And it always gets more and more complex. They add more. Somebody finds this, but it's going to influence this. But then if we take out this, it's going to do that. Because, you know, and the role of the physicist is to say, well, all this comes from one basic mechanism or a few that then automatically give you all the rest. Now, this is the physicist's point of view. But of course, there are other points of view. We say either you go from simple to complex or complex to complex. That's about the way I see it. And I'm sure that this must not, maybe not the right way to see it, because I come here and it's always more complex. To me, maybe I'm wrong, it's getting simpler. But I think that we should have a direction from the basic science, and at least we should have the very basic interaction of radiation with matter. We should get that right. And what it produces, these primary particles, the first one to be produced by the high energy radiation, what do they make? What do they produce in the cell? Okay, once we have that, I think the subsequent chemistry is already there. And the biology too is there. It's just we say, well, we do this, we irradiate, and we have this biological effect. We don't worry about what's in between. And more or less the same for the chemistry. So, but the funny thing about this field, we don't know how it begins. Which is a bit like the creation of the universe, right?
Yes.
You know, we know a lot of detail about how we live here on Earth and how things are organized, how people interact, and the planet and all that. But how did it really start it? Okay, so in radiobiology, we really know how it started. You know, we know this ionization and so on, but these primary particles, how do they trigger the chemistry? Yes. And we have some big idea, and now I think we understand much more. But still, the big question now is, now that we have this understanding, we may have to gather more information, okay, but at some point we may be able just to link the whole field together. But at least we should know what's in the beginning.
So don't forget about physics, that's right.
Well, yes, because maybe it's a message for radiation research. But I'm sure it will go up again, and that this field will progress very, very strongly in the next 20 years. It's just, it goes back and forth. You know? But we all hope that this progress will be made in the Radiation Research Society.
So what an outstanding career. Thank you very much for telling us about it. So,
well, it's been my pleasure to come and say a few words about this.
Thank you. Thank you.
But maybe I should mention one thing, though, that this has not been done alone. And I had many people as chemists and a few radiobiologists, you know, in the department, people like Darrell Hunting and Richard Wagner, Benoit Paquette, you know. These were people that with whom I've worked, and now Brigitte Guérin, and so on. So it's impossible to do this and link it to biology or chemistry without having a group of people. And I think this is more and more integrated now, the research in the radiation, and I'm very confident that this will progress quite enormously in the future.
Great. Thank you very much.